Okay. This evening we have Dr. Kirsten Seibach joining us, Assistant Professor at Rice University in the Department of Earth, Environmental, and Planetary Sciences. She is our very own resident Martian geologist, which is pretty exciting. She's been studying the early landscapes and climate on Mars using the rover observations of rock composition and comparing that to analogous terrains here on Earth. Currently a member of the science and operations team for the Mars 2020 rover Perseverance, which is super exciting. It had a really exciting landing. We got to see more of the landing than we've ever seen before, so it was really neat. And so looking really forward to hearing the updates from her. So with that, I will hand it over to you.
All right, great, thanks. All right, well, hey, thanks for the introduction and thanks for having me. Let's see, we'll get started. I wanted to just kind of cover, what are we learning with these Mars rovers? I'll talk about some of the aspects of the Curiosity mission that were most important for setting up the Perseverance mission and selecting the landing site, and kind of what's going on with the Perseverance rover that landed just under 2 months ago. So let's see, get the laser pointer up. Well, okay, got my cursor at least. All right, so when we look at Mars today, right, Mars is the next planet out. It's quite cold. The atmosphere is about 6 millibars, so 0.6% of the atmospheric pressure we experience here on Earth. But despite the very thin atmospheric pressure, there is wind blowing across the surface of Mars today, and that's kind of related to this balance between atmospheric pressure and the greenhouse effect. So if you have a bigger greenhouse effect, you get to maintain temperature better. On Mars, the temperature at any given site will swing about 100 degrees between day and night. And so that significant temperature gradient causes wind. So we look over, it's windy, but otherwise pretty barren planet. And when we first got satellite imagery, it did confirm that at this point, Mars is relatively barren. The main albedo differences, the main color differences you see in these spacecraft maps are just based on where dust has accumulated in the light zones and where there's relatively dust-free darker zones. But you can see that there is ice at the North Pole and the South Pole of Mars today. And it doesn't look like much in this projection maybe, but if you were to melt all of the ice in the polar caps, it would be enough water to cover the whole planet in about 22 meters of water. And so there is significant water on Mars. And furthermore, there's clear evidence that there was more significant water on Mars in the past. And that comes in the form of clear water-created channels crossing different parts of Mars. Now, knowing that water was flowing across Mars in the past gives us a start, but it doesn't tell us that the record of what the environmental conditions were like when the water was flowing are recorded. What we need in order to investigate past environmental conditions are sedimentary rocks. On Earth, plate tectonics expose all of the ancient sedimentary rocks that form after debris is eroded, sediments are eroded and carried downstream or carried in the wind and accumulated in some kind of a basin and cemented. When we first got these images of channels on Mars, it wasn't clear, first off, whether sedimentary rocks formed, and second off, whether they would ever be exposed. There aren't plate tectonics on Mars. There's pretty much impacts and volcanoes are the main things that cause topography. And so what we weren't sure of, in fact, for decades, was whether there would be any sedimentary rocks to record the environmental history of Mars. That changed in the year 2000 with a seminal paper, and I'll zoom in on one of the locations that was highlighted in this paper. This is a couple of craters. These are craters that were cross-cut by those channels. So we see flood channels in a lot of different areas on Mars. These craters, we can see that water actually flowed into them and water flowed out of them. So they were part of the channel system where the crater actually filled up and was a lake. This larger crater that you see is called Holden Crater. And there's an older crater on the edge near Holden. This one's called Eberswalde. You can see that Eberswalde crater was actually partially filled by the ejecta from Holden Crater. And so this crater is older. But when the water flowed through, both craters were present, and water came in, it filled up Eberswalde. It actually came out the top right up here. And then you can see some of the channels right here. You can actually see one of the channels coming in, and I'm going to zoom in on this white box. So you have this little bit of a crater basin from this ancient crater, and you have water coming in through this top part. And here's what we see in the high resolution inset. What you see is an inverted delta deposit. So we're used to delta deposits like the Mississippi River Delta, where the channels are low and interchannels can be high, sometimes exposed and vegetated in the case of the Mississippi. And the channels are carrying coarser sediment, and finer sediment settles in between channels, and then the channels avulse when they fill up. What we see here on Mars are the deposits from those channels, and you can follow them, but today the channels are cliffs, right? And so this is an inverted deposit because the wind has actually blown away all of the material that was deposited between channels or on the channel levees and left only the channel deposits. And that wind has done a lot of work. It's cleared out meters and meters of stratigraphy and left these nice layers exposed. So if we were to send a rover to this location, we could drive through these layers and investigate what the different layers were that were deposited by rivers coming into this delta. So this is a great plan view exhibit of how sedimentary rocks are exposed on Mars. And so now that we know that the wind will actually do the work for us and expose ancient sedimentary deposits, now we know that there's a record on Mars of the past. And more importantly, that record is from about the time, it was from about 3 to 4 billion years ago. So that's really important. When we think of Earth, right, you've got, here's a timeline. So we've got from the formation of the solar system planets to today. We think of Earth, because of plate tectonics, Earth is constantly changing. And so most of the surface records about the last billion years. You get older and older, you get some really critical events in there with the rise of oxygen and evidence for early life. But once you get back to kind of this evidence for early life time frame, you know, on Earth, only 1% or so of the crust from more than 3.5 billion years ago is still preserved. And of course, it's been strongly modified during plate tectonics and during different plate tectonics episodes. We don't have any rocks older than 4 billion years old. On Mars, we only have dates on Mars because we can count the number of craters that have impacted different surfaces. And so if you know the size and number of craters that have impacted a surface of a certain area, and then you can compare one area to another. You can say one is older than the other because more craters have hit there. And then we use our calibration based on lunar chronology. So on the moon, we've actually been to different places exposed to crater bombardment and had astronauts pick up samples from different surfaces with different numbers of craters. So we use the and then we have radiometric dating of those samples, so we know how old the surfaces were. So we use that calibration from the moon, extrapolated to Mars. Mars is closer to the asteroid belt, so there's a little bit of a change there. But when we extrapolate that to Mars, we get a sense for how old different surfaces are on Mars. And it turns out water was flowing across the Mars surface right around that time when life was starting on Earth. So most of Mars' surface is actually quite ancient and preserves this time between 3 and 4 or older than 4 billion years ago. Furthermore, spectroscopic analysis, so looking at different wavelengths of light as they've bounced off the surface, has showed us that there's a higher concentration of mineral clays in the most ancient deposits on Mars, most ancient surfaces. There's excess salts, typically sulfate salts. We actually almost never see carbonate salts on Mars. There's only a few locations. accumulated kind of in the latter half of this active period on Mars between 3 and 4 billion years ago. And since about 3 billion years ago, Mars has been mostly dry. So that means Mars is actually an excellent place to look if you want to understand how geological systems work kind of in the absence of life or as life was forming on Earth. So we're excited about Mars not only because it might have life, and we want to answer that question, are we alone? But also as geologists, we're interested because this planet gives us a window into a time period that's really hard to sample on Earth, and kind of forces us to reevaluate our assumptions while we think about early Earth, right? In a lot of ways, early Earth is like another planet. And so this really helps us think about kind of ancient processes on Earth in a beautifully well-exposed environment. And so this picture just kind of sums that up. But when I'm thinking about Mars, I'm thinking about Mars at the time when Mars and Earth probably looked relatively similar and potentially both had rivers and lakes and oceans and glaciers across the surface. Critically, we are still interested in whether or not Mars was habitable at that time. And I'll talk through Curiosity mission, but I want to define habitable early on so I don't miss that. So we define habitable, right? The search for life has to be in some ways related to the search for life as we know it. And as we know it, life requires liquid water, the raw materials, as in the elements required for life. So carbon, hydrogen, oxygen, phosphorus, schnapps. It requires some form of energy. Now that can be a variety of different sources, chemical energy, solar energy, etc. And it requires somewhat favorable conditions. On Earth, life has adapted to a myriad of different ecological niches, but in general, we kind of need it to not be super salty or super acidic. We need that water to be available and probably a climate where that makes sense. The fifth factor is that we need all of these to be present for some extended period of time. If you really want life to exist or thrive in an environment, it must last for more than 100 years, right? It needs to be geologically relevant in some ways. All right, so in the pursuit of this, we first identified locations on Mars where liquid water or water had passed through in the past. And our first set of landing sites on Mars were pretty dedicated to this idea of finding the water. We successfully found water. With the Spirit rover, we saw hydrothermal kind of indicators. With Opportunity, we saw cemented sand dunes. With Phoenix, we found ice just under the surface, indicating that these glacial deposits or the ice caps are not the only ice. There's also subsurface ice throughout the northern mid-latitudes. So we found water. And I'll talk about first about Curiosity, whose mission was really to find habitable environments, and then about Perseverance, who's taking it a step further and searching for signs of ancient life. So with Curiosity, at this point, we've gotten, one of the themes will be just like improving our ability to land in different sites and our ability to assess different sites. But Gale Crater is really exciting. Gale Crater formed about 3.7 billion years ago, right in that time period that we're interested in. It's about 155 kilometers or 110 miles across. And when this crater formed, the impact was so strong that the rock in the middle of the crater rebounded up and created what we call a central peak in the center of the crater. You can think of a slow motion water droplet, right? There's a big rebound. The rock rebounded up and froze in that position. After this crater formed and had this central peak sitting here, it filled up with sediment, and some of that moved in rivers, was fluvially carried. Some of it was blown by wind. Maybe there was glaciers, maybe volcanoes and ashfall contributed. But the crater actually basically filled up with sediment, much of which, at least at the base, was lithified into sedimentary rock. And then the winds changed. And really this wind is a key thing that's different about Earth and Mars, is that instead of plate tectonics, we just have wind erosion. But the wind came back, and despite this crater being mostly filled in as a kind of full flat surface of some sort, we don't know exactly what it looked like, the wind started digging in. It started actually evacuating the deposits that had filled up this basin. And the wind is actually still working today. The wind is blowing the darker looking sand. Again, the contrast on Mars is between light, dusty material and dark material that in this case is actively being blown, so it doesn't have as much dust accumulating on it. So the wind is blowing in from this side, the south, and blowing this dark material, this dark sand, around to the back of the crater and actually out of the crater, even today. And so what this has done is that it's exposed these beautiful sedimentary layers. And so that was our goal with the Curosity mission, was land here, land in this flat area in kind of this moat around the central peak, and then go climb on these layers of Mount Sharp in order to assess the ancient environments that deposited the sedimentary rocks within this crater. And these layers were specifically chosen not only for the beautiful exposure here, but because this is one of the only sites on Mars where we actually have a stratigraphic a column, a stratigraphy that contains, from orbital observation, clearly contains those main themes that we saw in Mars mineralogy, which is the transition from phyllosilicate clays to sulfate salts to dry dust. So this was the site for Curosity. Curosity is about the size of a small SUV. There's a variety of scientific instruments. What it's designed to be is just like its name, Mars Science Laboratory. It's designed to be a roving laboratory that can actually acquire and analyze samples with pretty high degree of precision. It's got an XRD mineralogy instrument. It's got a mass spectrometer on board. It has a little drill so it can actually sample the rock and deliver the powder to the mass spec and the XRD. It also has some remote sensing instruments. The most fun, perhaps, in this image is the Chemcam Instrument, which is a laser-induced breakdown spectrometer. So we'll zap rocks between 7 and 20 feet away with this high-powered laser, zaps the top of the rock into a plasma, and then looks at the plasma with a spectrometer and detects the elements that are present in that rock. And so that's one of our survey instruments to help find the locations we can drill in. There's also an instrument I'll talk about a bit on the arm called an Apxs, X-ray spectrometer, that can get the composition of a penny-sized spot. So the laser gets a very small spot at, it's a little more qualitative, it's semi-quantitative, and then the penny-sized spot is slightly more quantitative, but then suffers from dust cover. So we have to work between these different instruments, but Curosity can really do a lot of analyses in place. And we found the right landing site. This was one of the outcrops that Curosity observed that was really critical in kind of mapping out the geologic context around here. The top image, these are two images of the same outcrop, but taken from different angles. So on the top image, the wall of the crater is off here to the right, and the center of the crater, the central peak, is off to the left. And so you're seeing the rocks that are being deposited from the wall of the crater to the right over to the left. The bottom image is actually sitting right here on the right side of the top image and looking at this same set of rocks kind of head on, as it were. And you can see that there's a bunch of rocks. They're pebbly sandstones. They're dipping away from you and stacked. And on the top image, if you look, you'll actually see that there's this nice, slide doesn't want to change. There we go. There's this nice kind of swoosh. So we're actually seeing some of the clinoforms as rivers coming from the edge of the crater are hitting a lake in the middle of the crater and starting to drop their sediment in small delta deposits right here. And you can kind of just see this swoosh clinoforms right in this particular outcrop. So this is a really kind of key outcrop. After this, we drove off, we continued to drive towards the center of the crater and actually reached the lake, right? And this lake actually lasted for a very long time in the middle of the crater. We've been driving through we've driven through about 380 vertical meters of stratigraphy strongly dominated by laminated mudstone. So, which has actually caused problems for our climate modeling. We didn't know that Mars could have sustained liquid water on its surface for anything near that long. So this is a long-lasting, really important lake that it frequently has millimeter thick laminations like you see on the right. It sometimes has thicker centimeter scale laminations. I'll say for the majority of it, it's fine scale laminated. Those laminations might represent barbs, they might represent something seasonal or event driven, or we're not sure, some kind of precipitation layer versus detrital layer. But we've been working through this deposit for a long time, and starting early on, the first thing that we could establish about this lake, and in fact about even a little smaller lake that we found further out in the crater, was that it was habitable. Right, this mudstone was forming in a lake that was neutral pH. I mean, it covered all of those components of habitability that we established early on. Right, it had schnops, it had all the right elements. It's liquid water. We can tell because there are phyllosilicate clays that formed in the base in the lake itself. And while those form, they kind of trap some of the water, and they're great for trapping organic molecules as well. Phyllosilicate are an excellent way to find organic material. And so in the layers of the clay, you trap some of that water. We heated it up and ran it through our mass spec, and we can say that it was liquid water. It was neutral pH. It wasn't a super salty lake. It did have the chemical energy for life in the form of redox gradients between different forms of iron and sulfur. And like I said, this lake actually lasted for an incredibly long time that we haven't even fully grasped yet. Furthermore, one of what I think was one of the most exciting things that Curiosity showed us was that, in fact, the samples in this mudstone do contain organic material. So the organic material is likely in the form, our best understanding of it is that it's in the form of a kerogen with sulfur bound to the carbon, or a lot of sulfur bound to the carbon, which would have helped protect it from radiation. What we saw was not the full kerogen molecule, but smaller pieces of it that broke off as we heated the sample in our mass spectrometer. And so we saw kind of a variety of small reduced carbon, organic carbon materials with kind of all different structures, right, that are most likely, our best interpretation is they're breaking off of something like kerogen. Now, kerogen can be delivered from a meteorite impacting Mars. But what this does tell us is kind of two things. And one of them is that in this ancient lake, there were organic materials. So we don't know if there was life, right? But there was food for life, right? There were organic materials sitting there 3.5 billion years ago in a freshwater lake on the surface of Mars. Second, those materials have been preserved. It is incredibly difficult when you look at fossils or potential fossils or microfossils from 3.5 billion years ago to even get a set of scientists that can all hold the sample for themselves and go out to the field and see exactly where it was collected to agree on whether or not the organic material is a fossil from the ancient past, and whether or not the carbon signature is actually indicative of microbial life in 3.7 billion years ago, as opposed to something that's been altered by surface exposure or something like that today. And so for me, actually, even as a Mars geologist, I was kind of suspicious of our ability to find ancient life, even if it had existed on Mars. And this sample really at least pushed back on that for me, really changed my opinion a bit. I still think it's going to be hard to find. I'm not sure that life thrived on Mars and survived in a lot of places, but it is amazing to me that with only about 10 drill holes, this was early in the mission, with the first, we now have more like 30, but in the first 10 drill holes, we found 2 different sites where organic material was preserved from 3.5 billion years ago and was able to be detected with the mass spec on Curiosity, which is certainly not quite at the level of mass spectrometers we have here on Earth. So So with this in mind, we're really excited. I'm trying to get you pumped up for Perseverance. And I'll just note for curiosity that we have continued to drive through those layers. This is one of my favorite pictures, looking off at the layers where this mudstone makes up some of the key layers building up Mount Sharp. Right now, we're actually kind of climbing around here off a little bit to the left of this image and hoping to kind of wrap back around. We're interested in this kind of flat lying, well, it's not flat lying, it's slightly dipping erosion resistant interval right here. That's actually kind of at the base of a canyon coming down Mount Sharp. And so we're approaching this zone right now. But these layers are absolutely beautiful. And actually, one more, a close-up of where we are now, and you should really look this up. We've got a couple different models, a couple different angles of images on it, but Mont Mercou is this outcrop that we're currently looking at with Curiosity, and it's beautiful. It's got kind of some of the, we're getting towards areas where the lake appears to have preserved some evaporation indicators, and so climbing around on this outcrop. And just for scale, it's about 17 feet high, so 2-story tall outcrop here that Curiosity is investigating. Okay, so now I'm going to zoom in on one other reason why Perseverance's mission is so exciting, and that relates to actually the research that we're doing in my lab and maybe that you've done before. But what we're really interested in is untangling the full story of sedimentary rocks. And so we really emphasize the kind of source to sink picture. When you're looking at a sedimentary rock, it preserves the answers to a bunch of questions, right? It tells you about the source rocks, which on Mars are typically volcanic, how they were transported, the climate, and the cementation. But on Mars, we're restricted in some ways. So with Curiosity, we do have this roving laboratory, but our main tools for assessing the mineralogy and what the geochemistry mean are the XRF-based instrument that gets that penny size quantitative chemistry of the surface deposit, the laser that zaps little spots in a grid or a line across a rock at high resolution. And when we drill a sample, we get XRD analysis of mineralogy. But we actually do this quite rarely. And so for example, in the river deposits where I showed you the Cobley sandstone in the fluvial deltaic zone, we had to get about 110 samples like this of penny-sized spots before we could really start to untangle all the different components building up the inside. Now, some of those, sometimes you can get 2 and start to answer a question, but to answer the full question of what was the source rock like, we needed about 110 of these samples. And one of the key things was just that minerals were sorted during fluvial transport. And specifically, we had coarse plagioclase grains and fine mafic grains, which tells you something about the volcano. So I had a student working with me, a postdoc working with me, and she looked at exactly what minerals were enriched in the coarse grains and showed that it had to be fractional crystallization of plagioclase. And if you look at the plagioclase and also look at the full set of minerals that we see in this unit, we're not just sampling from one volcano, we're sampling from, potentially different fissures, but also 2 volcanic evolution sequences, 2 different episodes of partial melting of mantle material and development of magma. Furthermore, the fact that we could tell exactly what the source was like and what these minerals were indicates to you that these are pretty close to primary igneous minerals that we're seeing in a sedimentary deposit. And so we saw very little weathering. So we tried to assess, our next task was to try to assess what was the weathering like that left these igneous minerals so close to intact. And so I had another student, a postdoc, Mike Thorpe, who's now at NASA JSC, and he looked at basaltic rocks all over Earth. And so the dominant thing that controls basalt weathering is temperature, climate. And so the temperature of Jezreel Crater, when these rocks were forming, is most similar, according to the degree of chemical weathering, to Iceland today. So it's pretty cold. And we're doing further work to look at kind of what cemented the materials together and actually made a sedimentary rock and made zones of higher alteration than others when we had these kind of cold climates and unaltered igneous rocks, unaltered igneous minerals. What were the groundwater like? What was the groundwater like? Excuse me. And we hope to pursue a similar set of tasks with Perseverance. With Perseverance, we have one higher resolution instrument called Pixel. Pixel will actually not just get chemistry of a penny-sized spot. Instead, we're going to get a map within that penny-sized spot. So they compare it to a postage stamp for that instrument, but we've got a postage stamp, and we'll actually have a map of minerals and actually be able to map those compared to the layers in the rock. And so I'm working with a team at Rice we've generated an algorithm to identify any minerals that Pixel happens to coincidentally hit. And we'll use that to go into some of the same details that we've been able to with Curiosity. But as you know, as geologists who worked on Earth, right, all of this is great, but it's solving different puzzles with a very different set of tools. When if we could bring those rocks back to Earth, we could slice the thin section and look at every clast, and we could look at every mineral that's in there and actually, describe really a lot of what happened to that rock. And especially if we had one of these rocks back on Earth with the geologic context from the mission. And so that's Perseverance's real goal. Perseverance is step one in Mars sample return. So Mars sample return is a huge decades-long project with NASA and the European Space Agency teamed up, where Perseverance will collect samples and we'll actually put those samples, they're going to be kind of finger-sized samples that will put in sealed tubes and deposit on the surface of Mars. So there will be a collection of carefully selected, geologically described, sealed sample tubes on the surface of Mars, and we'll send some follow-on missions. We'll actually probably send all of these at the same time. 2 of them will land on the surface, and that'll be a paired mission where there's a Mars ascent vehicle and a sample fetch rover. Mars ascent vehicle lands and stays in one spot. Sample fetch rover drives over and grabs the samples that Perseverance has left on the ground and returns them to the Mars ascent vehicle. It packs them into kind of a basketball-sized small rocket, which will then be the first thing launched from another world. It'll launch off of Mars into orbit around Mars. We can't launch it quite all the way to Earth, but we'll have sent a second mission at the same time as these ones, a Mars orbiter that will come from Earth. It'll orbit Mars, wait for that basketball to come out into space, grab the basketball, grab this set of samples, and then actually return to Earth with them. And at that point, crash carefully somewhere in the Utah desert, and we will go pick up the samples and actually have our first chance to analyze these rocks with all of the tools we have here on Earth. And so with that context, you can see where it was really exciting to even be part of the question of where will Perseverance land? Where is the one spot on Mars that we're going to go pick up samples, and those will be the first ones returned to Earth? Where can we find one spot? If you had Earth, right, and you got to go to one spot to collect samples to bring back and say what happened to Earth, it's a challenging task. And so I'll show you the site we picked. Keep in mind we had established with Curiosity what habitable lake environments could look like. And we had established with previous missions that there were also hydrothermal environments that have been discussed as potentially habitable. Okay, so here's the bigger context of the Jezreel landing site. I've got to get a high resolution picture here, but of the Mars globe, you can see the topography here where red is high and blue is low. It's not water, just low. You can see that, in fact, major topographic areas are defined by impact basins. Relatively spherical or round low shapes are impact basins. And one of the big ones is called Isidis. This is Isidis Impact Basin. It formed about 3.9 billion years ago. And after it formed, so this is one of the most ancient, one of the really ancient impact basins on Mars. So this would have thrown up a huge amount of breccia. It would have created a large hydrothermal system for any water that was in the vicinity when it impacted. So there would have been, lots of big megabreccia chunks of different materials of Mars crust, Mars early crust, interacting with this hot water all around the Isidis Basin here. Now, Jezreel Crater formed kind of on the rim of the Isidis Impact Basin right here. And we will zoom in on the key feature in Jezreel Crater. Jezreel Crater actually, like Holden and Eberswalde, it was a crater that streams ran into. They actually did fill up the crater in this case and flow out the other side. So Jezreel Crater has both inlets for water and outlets for water. So the area that we've selected for landing is kind of this blue circle, and actually the star is a giveaway where we landed here. But you can see it's over on the west side of the crater. This white zone is the crater rim, and you can actually see this river channel that flowed in and then formed a delta. Here we go with higher resolution imagery. So here's the river that flowed in and formed a delta, and this is again inverted topography, just like we saw at Eberswalde, where the channels have now caused some zones of this to be preserved. They have resisted the wind erosion that has taken out other material that was surrounding this delta. The floor of the crater, we don't have a good description. It's mafic, so it looks volcanic potentially, but could also be like Curiosity saw, sedimentary rocks that are pretty close to their volcanic sources. And I will tell you more about this landing site. Couple more angles on this so you can see the topography, the imagery. This is spectroscopy. A key thing about the Jezreel site is that the lake in this crater appears to have precipitated, well, we don't know that. We've seen carbonates at Jezreel. It's one of the only places on Mars where we see carbonates. We actually see two different types of carbonates. One of them is associated with olivine, and it's throughout this region, so it's regionally distributed. And so probably not associated with the lake. The other is preferentially exposed around the crater rim and looks like, hopefully, looks like it forms a little bit of a bathtub ring, and so probably was a precipitate of the lake in Jezreel Crater. We also see phyllosilicate minerals, again, those clays that are really good at preserving organics, and a variety of igneous minerals. And we have spent a long time mapping out these different deposits. I wanted to show this one in particular. The next thing I'm going to show you is the landing video from Perseverance landing. I don't have the sound with it. I do recommend watching it with the sound as well. But I'll just talk through part of what we're seeing as we're landing. And so from this map of the crater rim and the area that Perseverance, is actually landing, a couple of things to point out. There's this zone called Seta. The names are from the Navajo language. And what I want you to see is that it's shaped kind of like a mitten or a dog bone here. And there's a little crater on the side. You'll be able to see this as the rover was landing, right? And there's a little crater over here. One of the other major features is that the edges of the delta are really, really sharp. And there's actually a few features, kind of plateaus. There's one right over here, and there's about 3 right over here that we call delta remnants that appear to be extensional parts of the delta that were also preserved from wind erosion, presumably by some kind of erosion-resistant capping material or harder cemented sandstone. And so as we were landing this mission, the only reason we got to land in this site, if you're an engineer, you're looking for a flat place. If you're a geologist, you're looking for a cliff. We always have to find a balance in between. The reason we were able to land at this site with this mission is because this mission had something called terrain relative navigation. And so it had a radar system as it was landing, as you can see the video from the bottom of the rover, and you actually know the rover is going to be looking for a flat, safe landing area. And we had pre-designated a bunch of areas in this blue circle that we thought would be safe to land. So with that, let's watch the video. All right, February 18th, just about 2 months ago. This is the command center at JPL. Most of us were spread in our homes around the country and around the world. First thing you can see is the parachute deploy. parachute is a supersonic parachute. It has to deploy at supersonic speeds. So it's made of basically Kevlar and nylon. It's made of kind of bulletproof vest material, and it was beautiful and perfectly successful. This next thing, that's the heat shield. So as Perseverance entered the top of the Mars atmosphere, it was moving at 12,500 miles per hour and obviously had to slow down. The strong friction at the top of the Mars atmosphere was absorbed by that heat shield. And so the rover was protected from that heat. Now you can actually sort of see it crash if you follow along, or we'll see what the crash site looks like in a bit. Okay, so some of the topography we're going to get, these little mounds right here are the delta remnants off to the edge. Up here, showing up in the northern part of top right-hand part, you can actually see parts of the delta. And right over here, you can kind of see that mitten shape. This is Zeta. Now Zeta, as we zoom in, and there's the little crater on the side of Zeta and the crater on the other side. And we're following, these are the cliffs right at the edge of the delta. There's another delta remnant, just went off the screen to the right. We're kind of wiggling around here because we've got a camera right on the bottom of the rover and it's dangling from that parachute. And so as the parachute kind of moves in the wind and the rover moves relative to the parachute a little bit, the camera angle is kind of moving a lot. You can actually see this Zeta zone has a lot of sand ripples crossing it, sand ripples, sand dunes. It's considered a not optimal place to land. Okay, so that jerk that you just saw where the camera kind of swung, here's the delta again, going back towards Zeta. That jerk was from actually separating from the parachute and switching to powered descent, which means the rover is now actually being carried by jetpacks by the descent stage. The rover is still close to the descent stage, but it's holding it with jetpacks and slowly migrating to the area originally identified as safe to land, right on the edge of Zeta. As we get closer, those jetpacks will start to blow the dust off the surface. And so you start to see the dust get blown, and then we get another angle because we're going to separate the rover from the descent stage. It's so cool. I got really excited. Okay, the descent stage is up there. It's the first actual alien flying object on another planet, right? And here's the rover being lowered to the surface with a data cable and some tethers. Those broke, and the sky crane flew away. We don't have any more imagery from there because the data tab was broken as well. But the rover was perfectly safe on the surface in exactly one of the zones we had identified as safe to land. And so it's a perfect landing. And actually we can get imagery from satellites orbiting to see where all the different components crashed. So this is the parachute. You can actually see even the colors on the parachute and back shell. This is the descent stage. So that's the thing that carried Perseverance down to the end, and it had a little extra fuel, which is why it had such a large explosion. The heat shield is off this side where it crashed after protecting Perseverance from the entry friction. And here's Perseverance. And you can see that actually the dust has been blown away from those two patches where we saw it blowing away as we were landing. And so it's caused those areas to be much lighter toned. And again, the rover's about the size of Curiosity. It's about the size of a small SUV. This is one of the first images. It's from a fisheye lens at the base of the rover that we use for hazard avoidance. And we called this the Octavia E. Butler landing site, following from previous missions, following from the Curiosity mission in terms of naming landing sites after science fiction writers who were visionaries who thought about, how we could envision ourselves on the surface of other worlds and in other times. What you can see initially is that there's a couple of rocks that have been really well exposed here. So there's a bunch of rocks kind of poking up above the dust, partially because we blasted a lot of dust and dirt away from this site during landing. You can also just start to see kind of the rim of the crater and part of the edge of the delta. Here's a 360-degree mass cam panorama, and I'll zoom in on part of it. It's actually really high resolution. You should really pull it up on your computer. It's available on the NASA site. But here are the two blast zones. You can see that the color of rocks is a little bit tricky on Mars. And so in the blast zone, you can see the most of the dirt is darker, regolith is darker. It's lighter in the blast area, which may be exposing material below this darker cover, but then the rocks are kind of multiple shades here. So some of the rocks are really dark, some of them are quite light, and some of the rocks in the background are a little bit harder to see. And I'll zoom in on a couple of them to show you. But what I want to zoom in on first is this area right back here. So this is our destination. This dip in the crater rim way out here is the channel that was carrying water into the crater. And so that dip is Neretva Vallis. That's where water was coming in. And you can see that that water created this delta. And you can actually see exactly what we kind of expected, that the delta is protected. It's been protected from wind erosion by some kind of a coarser sandstone layer capping unit. What you also see are, a small series here in the foreground and mid-range. These sand ripple deposits are part of that seta, kind of mitten dog bone shaped thing, and they will cause a problem for driving the rover. And so we actually will not be able to drive straight from this landing site to the delta, even if that is something we're really excited about. We're going to drive around the seta zone with all of these sand ripples and sand hazards so that we can actually drive more efficiently. Luckily, that might put us closer to one of the delta remnants, which are beautiful. When we look closer in the foreground of that mass cam image, we can see a couple of the rock types exposed here. And the lowest, there's kind of a few different rock types. There's one that's very flat and kind of the two things that, okay, I've got a note for myself here. The two things that you want to highlight when you're looking at Mars pictures, and especially in contrast to Earth pictures, are that wind erosion, aeolian erosion, and dust can really bias the way you think about things. So these appear to be light-toned flat rocks, relatively light-toned, but kind of multi-toned holy rocks, we call them, full of holes. And you can also see even off in the distance that potentially those tone differences are made up by dust cover. This is a rock that's been significantly affected by wind-blown erosion. You can see that this zone is well eroded, and this zone is now overhanging on this rock. We call it the harbor seal over there. And we've gotten some further analyses on these rocks. This is a high-resolution image from the SuperCam, which is just like the Chem. It's better. It's got a few more gizmos and gadgets kind of thing, but it's similar to the laser. It's very similar to the laser instrument. So we've zapped a couple of these rocks, or we've taken high-resolution pictures of them, but right now we're still working on a lot of engineering checkouts. And so basically, in order to, we've zapped some rocks with the laser, but we haven't fully gotten to calibrate this laser working on Mars yet by targeting every one of our calibration targets that we brought with us, so that we make sure that our quantification of the elements is based on quantification of elements on Mars under the conditions that this laser is experiencing at this time. From comparisons to other instruments on Earth and things, we're saying, okay, a lot of these rocks are generally made of basaltic minerals, but we really hesitate to go much further than that because we really need to get that quantitative calibration done. That involves a whole lot of different checkouts of the wheels, the arm, the instruments, calibration devices, etc. This I just snuck in because it's one of my favorite. I love these pictures where you get to see one of the key things to do was to check that we could drive. This picture shows the tracks just starting out of kind of nowhere on Mars, because we did drop from a helicopter onto this site. This is one of the delta remnants that hopefully we'll get to go visit. You can actually see there's kind of beautiful stratigraphy preserved here that'll be really exciting. And we'll think about how to go visit that. The real challenge, again, is getting around SETA to figure out which way to go. So to give you an overhead view of that problem, we landed right here. This zone is Zeta, so we need to either go on a northerly loop around the top of the mitten, as it were, or on a southerly route down to a different zone where we can actually drive across here, and where we might be able to visit this delta remnant that you just saw, Kodiak. There's Kodiak. So that's this guy. There are also delta remnants right up here that'll extend this northern route. So this is currently our first real debate as a team, right? Because which route you take, just like which landing site you pick, defines what samples we will collect on Mars and bring back to Earth. And that is really the major goal of this mission. And we have spent a long time with the team looking at all these different routes, figuring out which routes are traversable, which ones we can drive on with the rover, and what units those routes will visit. And so we have kind of hypothetical sample caches built up of all the different types of deposits that we may be able to visit, like the Fluor unit, that olivine carbonate regional unit, the delta deposits, some of the regolith or dirt, point bars or channels or lakes. We want to collect all these different things. And we really have to balance it out carefully because we have a limited number of sample tubes. The return basketball case that they're designing now holds approximately 30. We have 43 tubes, so we have some that we won't be able to take with us, but we'll probably have to leave some in Jezreel Crater as a safety. Oh, let me map that out for you. Okay, so we landed over here in Jezreel Crater on the ellipse to the right, and we realized we can actually drive. Part of the reason this site was chosen is because we can actually drive out of the crater. The rim is not too steep. There's a couple of paths we can take. And if we can drive out of the crater, we can also go investigate those really ancient megabreccia blocks that would have been thrown out of the Isidis Basin and in hydrothermal systems on Mars. So think of getting to sample both this nice lake deposit and this hydrothermal, hot, volcanic, interesting deposit that would also be habitable and suitable for the origin of life. So what we'll probably do is double up on our samples while we're in Jezreel Crater, leave one stash of samples there, and bring the duplicates with us on a long journey out of the crater and try to see if we can collect a really, excellent mega cache and hopefully have that ready before the sample return missions, the follow-on missions, fly to Mars, which will be in 2026 or 2028. For right now, we're working on the helicopter. Ingenuity is a small technology demonstration. It's a 2-kilogram helicopter that was held beneath the body of Perseverance, and Perseverance dropped it down on the surface and drove about 13 feet away and looked back and took this nice selfie picture. Ingenuity is the first powered flight on another planet. I guess the landing descent stage doesn't count, but Ingenuity would actually be, as you know from your field work, using drones to map out areas ahead of traversing them, or in terms of getting a better context view of what you're looking at, they can be really helpful. And so this was kind of the first step, was to bring a small drone that we could fly and just get a sense for what it's like to fly in that thin Martian atmosphere. And so if Ingenuity works, which I sure hope it does, then future missions can have, drone companions and actually kind of work with them. In this case, we will not continue to bring Ingenuity along with Perseverance. Instead, it's kind of just to show that we can. Right now, the Ingenuity first flight has been delayed because of they need to make an update in the flight software. And so we were supposed to do that about 2 days ago, but it's been delayed about a week. And you should listen out for NASA News, because they'll do a live broadcast of the helicopter team reaction as we get the data back from that first flight. And with that, I would like to just take some questions. These two missions are actually 2,300 miles apart. They're not in the same zone, but I like showing the same rovers and Ingenuity's first flight in the same picture. So thanks for listening.
Great. Okay,
We did have a question from Jim Tucker. He asked, can either the dunes or the landing dust plumes give an idea of the Martian atmosphere, maybe of its viscosity?
Yes. Yeah, we will have a lot of different measurements. So we will have direct measurements from Perseverance of the wind, I guess, and we will use MOXIE, which is a little instrument on Perseverance, to try to convert the CO2 atmosphere into oxygen. So that's another technology demonstration that we brought along. And then, yes, observations of the sand movement can inform our understanding of the atmospheric viscosity and kind of the physics of how bed forms form on Mars. These are the ripples in Zeta are a little bit closer to transverse aeolian ripples, so they're not exactly active sand dunes, but they are kind of a mysterious bed form that we would be interested in investigating if we happen to come close enough to one. And the dust plumes will definitely be very carefully investigated by teams of engineers to make sure that we understand the dynamics of landing on Mars better for future missions.
I have several questions. First of all, thanks so much for coming back again. I was excited to hear the update. It was a great presentation. So that laser that zaps I don't understand. Is it taking a sample, or is it just mapping something out?
Yeah, so it's super high powered enough that when it zaps the rock, it turns a tiny spot into a plasma. So it's like just shooting one little tiny spot. It turns into a plasma, it creates this little plasma cloud, and we actually look at the plasma cloud with a spectrometer. And then you can see from the emissions within a plasma cloud in visible near infrared wavelengths what element components there are. It's a little complicated because different elements interact with each other weirdly. They're kind of strange matrix effects when in a plasma, but that's the technique.
Okay, so the other thing is, how long again does it take for this mission to get to Mars?
It takes about 8.5 months to get to Mars, and you can only go to Mars once every 2 years, which is why if you were this summer we had the Perseverance rover getting to Mars, the Chinese mission Tianwen-1 going to Mars, and the UAE Hope mission going to Mars all at the same time, because there's only a little window every 2 years that you have to face dynamics.
Okay, and then also, so you're stockpiled samples. So you're assuming that the weather or whatever elements there are not going to damage the stockpile? How are you protecting the stockpile?
Yeah, our main concern was really just thermal fluxes. So there can be some dust. Some dust may settle on the tubes, but that won't be, it's not a huge amount of dust. Actually, this Curiosity selfie that I've got on the screen was taken about 3 to 4 years into the Curiosity mission. So you can see we actually dropped dust on the top because we were dropping samples. So some of this was intentionally dropped by us, but different parts of the rover actually look pretty clean. The dust won't make a thick layer or anything. Sand does move, but again, moves relatively slowly, and we're not going to be, we won't put it next to an active sand dune. But the thermal changes are really significant. So the tubes were specially designed with an exterior coating to minimize thermal changes.
Because there might if those pesky Martians come by and snag them.
Or how long is the next mission that will actually collect those? I mean, are you talking 6 months, 2 years, or what?
So the best launch window for those two missions is either in 2026 or 2028. So I think NASA is planning to aim for the 2026 one so that they have a backup. They're kind of in that zone. And with that kind of timeline, we'd expect to get samples back to Earth around 2031, early 2030s.
Oh, wow.
So it requires quite a bit of patience. But we actually think, I mean, with Curiosity is still alive. They have very much the same body. Curiosity is running after 8.5 years. We're actually at 8 years and 8 months or so, right, on Mars. If Perseverance lasts that long, Perseverance could actually help. So potentially, if Perseverance hasn't dropped all the samples on the ground, Perseverance could go deliver some samples itself to the Mars Ascent vehicle. So there's a possibility that that those missions will, not interact and try not to hit each other, but they may end up being very close in time in that pickup zone.
So you're saying that the first mission, Curiosity, that is still there on the surface of Mars?
Yeah. Curiosity is still actively investigating. Right now, we're at that pretty Mont Mercou deposit, and actually, we've just climbed like partway to the top of it, which is cool. So we're actively working on both missions right now, with some overlap on the mission teams.
And then what you were doing on Perseverance is you were controlling the rover to actually collect the samples or say where the samples were taken?
Right now, we're waiting for the helicopter. But and actually, I got a question directly, I think, on the chat. But the team that decides each action is from around the world, and it is composed of. There's a few different ways to get on the team. The mission headquarters is at NASA JPL, and the first thing that they do is they have the body of the mission planned, and they request groups that designed instruments. And so instruments apply to be part of the mission, and a certain subset of those are selected. And so there's a group of scientists for every instrument who help develop the instrument and calibrate it and operate it. Later on, kind of much closer to landing on Mars, they do selections for participating scientists. And so participating scientists are folks like me who have worked with previous missions or study Mars or study Earth and have kind of a different perspective than the people that are operating specific instruments. And we're kind of more of the cross instrument analysis and help contribute to the decision. And so overall, you end up with a group of something like 400 scientists from everywhere from Australia to France to Canada to the US to Russia to Spain, working on crazy time zones in order to collaborate to decide what the rover will do each day. And so different people have different tasks on a daily schedule. I'm working a lot with one of the instruments, the Pixel instrument team right now, but we haven't gotten any observations yet because we're waiting for the helicopter and for all of the instrument checkouts. But I will be part of that, and especially looking at the geologic context of different minerals as identified by Pixel or by the laser or by the Raman instruments that we have on board.
Thank you so much. That was very cool.
Any other questions out there? Oh, wait a minute. We have another one in the chat. Are you able to see that, Kirsten?
Yes.
Okay.
I see it at the current moment. Okay. Will we be able to see a high-res view of said structures in the channel sands? I sure hope so. I think we can see just a little bit from where we are, and we're trying to take things at different times of day. We have a couple of zoom cameras, sort of the main cameras on Perseverance are zoom cameras. And then we have the high-resolution camera that comes with the laser instrument and the high-resolution camera that we use for selfies that's out on the arm. So I think we will kind of play around with what we can see in the channel sands, in the delta remnants, and in the delta itself. But we also know that we will be driving towards those, and so we will definitely get better resolution imagery of those as we get closer. And so I'm not sure. There may be some early papers kind of predicting what we're seeing from a distance, but then we'll be able to do much better high resolution imagery of the structures as we get closer. And the effective wind over time, I see the last part of that question, actually, it causes some difficulty, but with Curiosity, we've certainly been able to still identify a lot of textural effects.
Oh, really cool stuff. And I do strongly recommend that you go Find the websites, find the YouTubes, watch the landing. I especially like the version that was done there in y'all's offices where y'all were adding your commentary and the excitement. That was just fun to listen to and watch. So,
Yeah. Oh, I see a question.
Another
There's
question?
a question. Yeah.
Yep.
Was atmospheric pressure much higher 4 billion years ago, and can liquid water exist under the current atmospheric pressure? So the answer is it cannot exist under the current atmospheric pressure, and so it must have been higher 4 billion years ago. But to what degree, we're still kind of hammering out with the climate scientists. So we keep going back and forth where the geologists say, hey, we found 300 meters of lake deposits. That means that we had to have warm enough climate for an extended period of time. But we're going back and forth because it's actually really hard to get Mars warm enough to sustain that liquid water. So 4 billion years ago, the sun was 75% as bright as it is today. And Mars, of course, is further from the sun than Earth. So it requires twice the greenhouse effect that we have on Earth today to warm Mars to sustain liquid water in the past, or an interesting combination of atmospheric gases. And that's kind of what we're getting into now, where if there's some reducing gases, then you can get a kind of induced stronger greenhouse effect than you can with just one or two greenhouse gases.
Okay. Well, thank you so much for joining us. I know we had, I think, ended up with the maximum 42 people, so we had a good attendance tonight. Obviously, a lot of folks are excited to hear about all that's going on out there. I know for me, it's just neat I just every once in a while pull up one of the 360 images and just sit at my computer and wish I had one of those virtual reality things so I could just sit on Mars for a little bit, because it's just so neat. But thanks for bringing that. Thanks for sharing that with us. Matt, you have anything you need to add?
Oh, I do have one more question. I was that spectrometer based colored photo.
Mm-hmm.
How did y'all do that? I mean, those colors were it enhanced the picture quite a bit.
Yeah, well, and it depends. You get to pick. It's a little bit tricky. You have to identify every time what exactly we've picked as the red, green, and blue. But it basically just looks across the visible near infrared spectrum of reflectance and says, okay, there's like a strong dip at 2.2, 2.1 microns because of H2O. And so use the kind of, so the red color, we use colors to help our eyes see the differences that are present in those spectra. And so if there's a strong absorption there, we'll use like the difference between the bright and dark and say that difference is now black and white, it's now red. And now this part of the spectrum, the difference between this peak and this trough is blue. And so if the difference is high, then you get a blue zone. If the difference over here is high, then you get a red zone. And if it's both, then you get a purple zone. But it's kind of a trick where we use color to visualize differences that aren't visual differences per se.
Okay.
We did have another question. Are plans being made for subsurface exploration, such as GPR, seismic, or reflection?
Yeah, and great, perfect question. The Perseverance mission actually does have a GPR. So there is ground penetrating radar now. So that will give us our first ground penetrating radar. That said, the Chinese mission is also planning ground penetrating radar. So that one hasn't landed on the surface yet, but we will hopefully have it from a couple of sites on Mars.
Cool. And then it looks like there's another one. Near the pole, is there any evidence for permafrost surface effects similar to what we see in Alaska?
Absolutely. Yeah, the temperature change effects cause permafrost kind of polygons at all different scales, depending on where you are near the pole. And so we see those, and depending on the thickness of the regolith above the subglacial ice deposits. And so we'll actually use some of those permafrost effects, understanding Alaska and the dry valleys of Antarctica as our kind of comparisons there to understand the thickness of the deposits above the ice.
Oh, but now we have an ingenuity question. How does it generate lift in such low atmospheric pressure? Well, I guess that's the question we're going to ask when we get to turn it on here in a few days, huh?
We'll see how it works, but it's got long blades relative to its side. It will move them quickly, and it has a very low mass. That is, I may not be the right person to fully answer that question, but it's been optimized the best we can.
So they use north, south, east, west. Y'all are using, how did y'all just kind of make up which way you think is north or south? Or I know this may be a silly question, but
yeah, well, there's no magnetic field, so it's not. But we do still use north, south, east, west, and we did have to define a kind of arbitrary elevation as sea level as 0, and then count all other elevations as plus or minus compared to that datum point. But it actually is a complex question, especially when you're working with smaller bodies. So if you work with people who work on asteroids, you really have to do a lot to define your coordinate grid in order to say where you are when you have especially non-spherical kind of bodies.
Hopefully we're sharing and agreed to a grid with the other folks that are on their way there, right?
Yeah. Yes, the base map data has been generated by NASA and made publicly available for a long time. So, so we all have the same base map.
Any other questions? Okay, with that, I guess we will adjourn for this month. Look forward to seeing everybody next month. Remember, get on the website and cast your vote for our officers, and I especially ask that you would consider casting one for me as one of the board members.
So Troy, you're running again. Did y'all have announcements at the very beginning?
Just brief ones, just covered what was on the website.
Because I guess I jumped on right at the last minute. I'm actually in Arkansas on.
Yeah, I was looking at that background behind you there. It didn't look like your house in Houston.
Yeah, no, it's the Ozarks. So so we were eating dinner and I was like rushing back to catch the talk. So, and I wanted to say hello to Lynn Travis if you're still there, Lynn.
Andrea.
Oh my gosh. You need to give me your information. I haven't seen you in forever.
No, let me type my contact information into chat. Everybody will get it, but that's okay. We got to talk.
Okay, so Troy, are there not, like in my Zoom meetings that I go to, you can actually pick a specific person to chat?
Yes, you can. It's in your chat at the bottom. It has a 2 and it says everyone and a little arrow beside it. If
but the only thing is there is
oh, you can only I can do that as a host, I guess. Okay.
I'm gonna send you my cell.
Send it to Troy and he can get it to me.
Kirsten, it was just a fantastic talk. Thank you so much. I just feel your enthusiasm, and I just am just so thankful that you're taking us along for the ride. Thank you. I heard your talk earlier. Was it before? It was definitely before the landing. And so when I saw you on the agenda, it's like, I got to hear what's happening next. So thank you.
Well, thanks. It is a fun ride.
Okie doke.
Oh wait, don't let me get Lynn's number.
For those who may have an interest, AAPG is hosting, the Women's Network is hosting a Geology of Wine presentation on April 16th. And they say to participate in the tasting portion of the event, you can purchase your own wines, and they have a specific list if you're interested in that. So that might be something of interest. You might have to search around on the AAPG website to find that. And the cost of the course is free, except for the wine, which you have to purchase on your own.
So Kirsten, I'm not sure if I'm pronouncing your name right. Kirsten.
Dr.
Siebach.
Siebach, yeah.
I'm sorry. I'm so sorry. So how long will you actually be working on this particular mission?
So I was selected at least for the first 3 years, and then they'll probably do another round of selections or different things. So hopefully.
And you just started, so you have several more years. Is that correct? So you'll.
Yeah.
Oh, that's so awesome.
What
an exciting field to be in.
Yes, it requires some patience, but it's a lot of fun when you can be involved.
And then your students, you have a lot of different ideas for research for your students, and where they can help you out and all.
Yeah, we're working on. It's exciting now that we have multiple missions. So we've got students working on Curiosity, students working on Iceland projects, and students working on Perseverance. So,
nice.
An exciting time for sure.
Yeah, definitely.
Got it. So Troy, do we have a meeting for May?
Yes, we do. We have a PhD student from Rice that is going to be talking about urbanization effect on water quality. I think, is that what I said? I just went blank.
I think so. Urbanization on water quality.
Yes, I believe that is correct. And I've also lost that page. But yes, it's already on the calendar, and you should be good to go. Just hit the HGS site, and you can find the information.
Okay.
Yep.
And then maybe in the fall, we'll have your student try to talk.
Jessica.
No, she'll still be at Rice in the fall, but as a master's student.
She will be at Duke as a master's student.
Oh,
and
okay.
we were looking at maybe seeing if we could plug her into June if she's ready. So we'll
keep a slot open for her.
Yeah, we still have June open.
Yeah.
And if that didn't work out, who knows? Maybe we'll all go rogue and have a picnic or something.
No, but we will definitely keep a slot open for her. So she just needs to tell us when she's available. We'll plug her in.
Oh, she'll be really excited about that. She's doing drones on Earth, drones in Houston. Very different from me actually, but she's kind of pulled together quite a network of advisors around here, and it's a cool project. So